EyeVLA introduces a leap in robotics by giving machines an active visual system that can look around and zoom with intention. Developed at Shanghai Jiao Tong University, EyeVLA enables robots to actively perceive their surroundings rather than passively record them. The system consists of three parts: a pan-tilt unit, a zoom-capable camera, and a smart multimodal brain that fuses image and language to drive actions. With the ability to pan and tilt, EyeVLA can adjust the gaze to keep targets centered while changing focal length in real time. The system translates every intended movement into compact action words, enabling efficient, semantically rich instructions for the robot. A key capability is real-time, closed-loop observation, where the robot continuously evaluates what it sees against spoken instructions. In a typical scenario, a vacuum robot could inspect beneath a sofa for hidden toys by adjusting its view rather than squeezing into tight gaps. EyeVLA makes this possible by voluntarily adjusting depth and angle to capture details that static cameras miss. The technology unlocks new efficiency in warehouses, allowing robots to locate items without moving positions simply by reframing their view. In manufacturing, EyeVLA can inspect tiny components for defects by zooming in and circling the target with precise focus. EyeVLA's flexibility also aids pharmacies, helping pharmacists quickly locate medications in cluttered shelves. The first author, Yang Jiashu, emphasizes unprecedented autonomy in open environments driven by language-guided visual perception. EyeVLA analyzes the meaning of spoken instructions and plans how to move to keep the target centered in the frame. It calculates how much to rotate and how much to magnify to make the label clear and centered. The process is continuous and self-contained, much like zooming in on a map by dragging and exploring details with a mouse. EyeVLA's architecture blends imitation learning with reinforcement learning, using real and synthetic data to teach language, vision, and action. In the first stage, researchers recorded human operators' gaze and actions, then generated synthetic data to align language, vision, and action. In the second stage, the model learned through trial and error in the real world, receiving rewards for successful, clear observations. Traditional robot vision is like a fixed camera on a tripod, unable to focus on distant or tiny details without moving physically. EyeVLA transcends that limitation by optically zooming and reframing to reveal fine text and textures from a distance. The team highlights the broad applicability, from small keys to complex medical workflows requiring precise perception. In a warehouse test, EyeVLA demonstrated the ability to reframe to capture critical details without relocating the robot. The technology reduces cost and complexity by learning visually from limited real-world data and synthetic simulations. Key takeaway: proactive, autonomous observation enables robots to operate safely and effectively in cluttered environments. EyeVLA's approach avoids the need for constant human control, allowing instruction-driven observation to be executed independently. The researchers envision broad impact from domestic helpers to industrial inspection and healthcare assistance. From finding keys to checking window seals, EyeVLA helps robots locate critical objects in real time. The core insight is to let robots actively seek information, much like how humans turn toward interesting details. In practice, EyeVLA uses a two-phase training method to reduce data costs while achieving robust perception. Yang Jiashu emphasizes that EyeVLA offers scalability and open-ended performance in real-world settings. The system's success demonstrates the power of optical zoom to reveal fine print on labels at a distance. Beyond small objects, EyeVLA can aid photographers and pharmacists by locating exact products quickly in busy spaces. The technology, instead of forcing the robot to move, learns to move its gaze to acquire the needed details smoothly. As EyeVLA continues to evolve, researchers foresee even more capable autonomous perception in everyday life. The core idea remains simple: let the robot see actively instead of passively recording a scene. EyeVLA's open-ended design invites further innovations in multimodal AI and robotic manipulation. This technology marks a shift toward truly autonomous perception, capable of making precise, context-aware observations. EyeVLA's approach reduces human oversight while expanding what robots can do safely in real environments. In short, EyeVLA enables robots to look, zoom, and understand, turning perception into practical action.